So thank you once again, and with that, I will hand things over to Natalie, who's a senior cloud architect from Zencore. Thank you.
Good morning, everyone. I hope everyone's got their coffees and has properly woken up. For the next half an hour-ish, we're going to be talking about cloud-native data platforms and their security. My name is Natalie Godek. I'm a systems/DevOps/cloud/infra/platforms engineer, whatever the next title for this role is. I've been lately architecting clouds at Zencore. Zencore is a boutique Google Cloud partner, and we go into our clients, our customers, and build cool platforms for them on Google Cloud and solve complex challenges for them. I have a specific interest in infra, data, and security, and I'm also a photographer, and you can find me on socials at @UVSuite. Let's set the scene for the challenge. We've been talking about data for a couple of years now, and everywhere you go, everything everyone is talking about is data or AI. And it's no surprise, because data is everywhere. Every company is sitting on so much data. And I think as an industry, we have come to a realization that in order to be a successful business, we need to know what to do with that data, and we need to actually actively do something with that data. So let's imagine you have an idea of a product, and you've built a prototype. You decided to do microservices, Kubernetes. Your microservices need to communicate, so you decided to do sort of an event stream. Maybe you use Kafka, maybe you use SQS or PubSub, and then it's successful. So you're getting more clients, you're adding more features, you're adding more microservices, all of them communicate. Nice, your idea is really taking pace and is progressing, and everyone is loving it. And as a modern, cool CEO and founder, you decide to give the power into the hands of your developers, and everyone can manage their own data stores. Someone needs a bucket, someone needs a SQL database, someone needs a NoSQL database, some cache here and there, some data transfers in other places. Nice, everyone is owning their infrastructure. And then you expand into different regions. And you need to serve clients in Europe, Latin America, North America, Asia. Each of those geographies needs their own data stores, so you're creating those there. You need to be close to the clients. You need to adhere to regulations in each region. You need to adhere to data locality. Okay, cool. You're doing all that. It's growing, and then you get this famous comics. Every cloud architecture comics by Forrest Brazil, where you have microservices, containers, managed services, mismanaged service, and unmanageable services. Data engineers got really excited and built a whole load of pipelines everywhere. You've got real databases and cool databases and a data lake that becomes a data swamp because nobody knows what's in there anymore. And it's just a huge mess. Nobody wants that. You want to try to avoid it, and luckily, the cloud providers, the big cloud providers, have a ton of cloud services for you to answer all of your data needs. Everything that you can imagine that you can do with data, there is a service for it. But wait, can you do that? I was once giving a talk about health tech data platforms in Switzerland. And the only question everybody in the audience had was, can you store sensitive data in the cloud? Like health data? Actual PII, PHI in the cloud? Is that safe? Can you do that? And the answer is yes, you can. And in fact, if you are on GCP, your cloud-native data platform and computation platform might look something like this. You might have storage in cloud storage, some expansive SQL database in Spanner, or maybe you don't need expansive, so you use Cloud SQL. Memory store for cache, your containers are in Kubernetes engine, they communicate over PubSub, because who wants to manage a full-blown Kafka when they just need some event streams? And then you want to plug in analytics, because we do need to do something with that data that we all sit on. You've got customer data, you've got logs, you've got event streams, the messages between your services. You need to figure out what to do with that. So you plug in analytics with BigQuery. And if you want to step that up and do something actually centralized and manage your data lake in a centralized manner, you would use Dataplex. Your pipelines are in Composer, your event-based pipelines are in Cloud Functions, and if you go ahead and venture into the land of AI and want to train some large language models, you would use Vertex AI. And if you're on AWS, your situation is very similar. You've got SQL in RDS, OpenSearch for search, some cache in Elasticache, some blob storage in S3, your containers are on Kubernetes, they communicate over, maybe this time you did decide to use full-on Kafka, so you use MSK, and managed Kafka from AWS. You plug in analytics, you use AWS Glue and Athena. Your pipelines are in Kinesis, and your large language models are being trained in SageMaker. Cool, awesome. But all of those services are public APIs. Each cloud service is a publicly accessible API. For the example of Google APIs, you've got the API itself, BigQuery, storage, or Cloud Functions, the path to it, and then the object ID. These are publicly accessible HTTPS endpoints, and you store your data in them. You no longer have, like in the on-prem world, you no longer have an actual server, physical or maybe virtual, but still on an instance that is in a data center in a private network that you can control access to. There is no such thing as instance of BigQuery. It's just data sets. They're serverless. There is no server. It's just in the cloud. That's not great, is it? We need to figure out how to secure those services, specifically serverless ones, because with Cloud SQL, with RDS, you kind of have your more traditional alternatives like security groups, and you have firewall rules, and you can have Cloud Armor to protect the network boundaries, but not with serverless ones. So let's have a look on how we actually secure those ones. Let's start with Google Cloud. You have a couple of projects. Projects in GCP are like accounts in AWS, and you have a VPC network. All of your instances that are in that network, like Kubernetes engine, like Compute engine, SQL databases, they will be inside your network. But as soon as you use storage, BigQuery, Cloud Functions, or anything else that is serverless, that is no longer in your network. And if an analyst queries data in BigQuery from their laptop, that is going over the internet. What do we do with that? In GCP, there is a tool called VPC Service Controls. VPC Service Controls is like a firewall on steroids. If a firewall works on levels 3 and 4, you have ports and IP addresses. VPC Service Controls knows the IP addresses, knows the authentication information, knows the identity, knows which laptop, which OS, which browser the request came from, which region it came from. Is the operating system updated? And loads of metadata that just comes with that HTTPS request. And you can control access to your resources based on that load of different parameters, right? The way you do it, you select the APIs that you want to protect. In this case, storage, BigQuery, Compute engine, and functions. And you select projects that you want to protect those APIs in. And you put all of that inside a perimeter. That is your boundary. The way it works is by changing the DNS resolution of the APIs. BigQuery is no longer accessible on bigquery.googleapis.com. It is now accessible on restricted.googleapis.com. And that endpoint has a specific IP address that is published. And if you need connectivity through a VPN from your on-prem environment or from your AWS or from whatever else, you can actually do routing so that all of the requests that are coming from an app that is running in a different environment, they will go through the VPN tunnel to this specific IP address. As soon as you've done that, all of the requests from the outside world are denied. And only those that you want and you specifically permit will be allowed. The requests from the outside world include the requests that are coming from the internet, but also requests that are coming from a different GCP project. Let's say you have a fourth project here that is not in the perimeter, and you want to query some data from there. It will be denied unless you specifically allow it. The way you can allow different things, you have 3 options. First one is bridges. Bridges allow you to connect 2 projects in different perimeters. Maybe you want to allow communication. Maybe you have an orchestrator running in one perimeter and your Kubernetes cluster in another, and you want to orchestrate something. You can connect them with bridges, and that will allow the communication between different perimeters. The next one is access levels, and that's really how you define how users typically access your environment. A very typical scenario for this is your internal VPN, corporate VPN IP ranges, your corporate Wi-Fi IP ranges, something that is known and managed by you in terms of network. Another one is service accounts. The previous session touched on service accounts and over-permissiveness of them, but sometimes, like if you run Terraform, chances are that you have a service account with owner permissions because that's just the reality of it. You need to manage the entirety of your infrastructure. Well, you will have admin level permissions on that. And if you have the CI/CD somewhere else, like you use GitHub Actions or maybe run your runners somewhere else, you have a Jenkins somewhere on-prem, for example, you can allow that specific service account to enter the perimeter to manage the resources in it. Very often, data catalog tools that are third-party, like SaaS tools like Datadog and Dataplex? No, the other one. Anyway, and the security tools, like if you use a Wiz or DivvyCloud or something like that, if there is communication between the third party and you, there will be a service account identity that you can allow for those types of communications. If you can combine both, IP address and service account, that's even better because then if one is compromised, you still have the other condition. And the last one is ingress and egress policies. And the way these work is by allowing you to define a specific API call that can go to a specific resource from a specific source. So for example, if you want to do centralized logging, you can allow the ingress and egress policies on all of your perimeters, whereby you allow the logging API calls to exit perimeters and go to a centralized place. And in that centralized place, you allow them to come in. And you know that this is only for your logs that are going to your central logging account. Another use case for that is if you want to establish data sharing between different organizations. If you have a partner organization, you cannot do bridges between orgs. So you can only do ingress and egress policies. So in that case, if you're sending some data to your partner, you will establish an egress policy on your side, coming from a data sharing project on your side with a specific identity and going into the recipient project on their side. And that's the only thing that will be allowed. It's nice and fine-grained, and it's like the latest addition to VPC service controls. And I was like on the centralized logging example, I was really lucky because I was setting up centralized logging in my organization at the time. I think it's been 2 years. And they released ingress and egress policies the week I was setting it up. And we had loads of perimeters and projects without perimeters. And it would have been such a tangled mess to set it up without ingress and egress policies. And the week I want to do it, they released these policies. I was very happy. But look, I know that VPC service controls is a tool that most people are a little bit scared of, or like they have had trauma, they have PTSD, they've seen the errors, they don't want to work with it anymore. But as soon as you kind of understand how it works and understand how to debug it, and big hint, it's all in the logs. The log message of an error contains all of the information you need to debug it. And once you have architected a nice and clear vision of how your perimeters are structured, you're really good to go. It's really your best friend against data exfiltration, against people copying data from prod to dev, your best friend in making sure that your data stays in the region where it needs to stay and is being accessed only from the region that is allowed. For example, health data in the US, only people that are physically on the US soil can legally access health data. So this allows you to make sure that only requests that are coming from the US are able to access your data. The best practice, you don't have to do this, but it's the best practice, is to separate your compute from your data from your research space. What do I mean by that? Your microservices, your Kubernetes, your operational data stores, like databases that are required for the services to run, your kind of event stream between services, you put them in one perimeter. And then you separate your data lake or your data warehouse into another perimeter. The services that are generating the data can write data into your data lake, but humans can only read it, and you never allow anyone to modify it, except in exceptional cases. I don't know, GDPR, someone has sent a deletion request. And then your research perimeter, that's where your humans work. That's where your data analysts, data scientists, data engineers do their work. That's where they explore the data, they can modify it, they can copy it here and there and do experiments and run pipelines that will never see production and that will never modify production data. That way you have established a real separation of concerns. Your gold standard organization data will never be modified by accident by a human, and the only pipelines that go into that space have been vetted and have been approved for use in production with production data. And then you connect different places with bridges or access levels or ingress-egress policies when you need that. And you can also cut that connection as soon as you need to. Now, yesterday there was a session on serverless and serverless compute specifically. And you would think that if you run serverless pipelines in like Cloud Run or Cloud Functions, and you run serverless data stores like BigQuery, and you run them both in the same project, and you put them both in the same perimeter, they should talk to each other, right? No, they will not. It will fail. Why is that? They are both serverless. What's going on? I'm putting two serverless APIs in a perimeter. Why do they not communicate? You see this beautiful error that everyone who has ever worked with VPC service controls knows way too well. Request is prohibited by your organization's policy. Why? Well, turns out serverless is not really serverless. It still runs on some network somewhere. It still runs as a task on an instance somewhere. It's just not in your VPC. It's not in your project. Well, it is in your project, but it's really not. So when BigQuery API, when the restricted API endpoint that receives a request for BigQuery sees this request coming from a Cloud Run service or a Cloud Function, it sees it as coming from a different VPC, from a different project. And that is denied because that VPC and that project are not in your perimeter. And in fact, you don't know about them. And you have no vision and no visibility on those VPCs and projects. You cannot add them into your perimeter. How do we fix it? You have two options. One is to take the identity, the service account under which the particular service or function runs, and add it into an access level. One way to automate it with Terraform would be, for example, if you have a module for GCP projects and people use it, your users, your devs use it, you can detect when someone has included enabling a Cloud Functions or Cloud Run API and generate a service account for that project specifically and tell your users, okay, if you use these services, you can use this service account. This is not ideal because ideally you would have a service account per service, per process running, per function. But if you want to completely automate it, you can do it that way. Another way to do it is to have a subnet, have a VPC, and the first option exists if you don't have a VPC at all. And I don't always want to manage VPCs and subnets if I'm using only serverless. But if you do have subnets and if you do have VPCs, you can use something called a serverless VPC connector. You deploy it to a subnet and you tell your serverless compute process, run or build, not sure, but Cloud Functions for sure, to use that connector. And in that case, the process gets an IP address in your subnet. And in that case, the request will come from a known subnet because it's in the same project. Cloud Run actually now has a native feature like that. You no longer need a serverless VPC connector for Cloud Run. You can just use VPC egress, and it's natively available within Cloud Run. Very handy, no more configurations that are kind of excessive. What about AWS? What do we do in AWS? It's the same thing there. If you have serverless services like, well, your S3, your Lambda, your CloudWatch is also serverless, SQS is serverless, CloudTrail is serverless. They actually, AWS do something quite cheeky. The communication with those services between like S3 and a container running on EKS in your VPC, that communication will go out of the AWS boundary into the internet and then back into the AWS boundary into S3. last time I checked. Maybe they changed it now, and if they have and you know, please let me know and we will rejoice. But last time I checked, it was like that. I'm like, why do you do that? Why does my container that talks to my S3 bucket that are both in the same account, why does it go over to the internet and then back into AWS? That makes no sense. But yet they do that. How do you prevent that? You use VPC endpoints. Similar scenario as with GCP's VPC, serverless VPC connector. You deploy a VPC endpoint and a bunch of routes that tell the services in your VPC, in your subnets, to talk to these serverless APIs via the connector, the endpoint. And then the communication stays within AWS network. And happy days, it doesn't go to the internet. Another thing about AWS is that it doesn't encrypt things by default. Your encryption at rest and encryption in transit, you have to enable it separately on all data services. And this is an example of how you would do that with Terraform for AWS Glue. Glue is like a data cataloging discovery service. If you have a bunch of business data in S3, you would use Glue to discover the data, discover what schemas you have, what tables, what data sets you have, to then enable analytics with Athena. And you can enable encryption on different places, like 3 components here. You have your business data in S3, you need to enable encryption there. You have intermediate store in S3 again for Glue itself, for the catalog, so you enable encryption of the catalog. And then the Glue logs. Why logs? Why do we bother encrypting logs and protecting logs in specifically? Well, with data analytics, your logs will contain sensitive data. If someone is doing a massive SQL query, and I don't know if you've ever looked at SQL queries that analysts write, they're like really, really large. If you know the context of the data set and you're looking at a SQL query, you might be able to figure out who that SQL query is about, which population or even which person if you know the populations that you work with. So you need to protect them as well. Same for GCP, the query data access logs will contain the SQL queries. You have different options for enabling encryption. You can use built-in AWS, so SSE S3, server-side encryption for S3. In that case, you don't need to manage keys. Or you can like manage keys on your own and have rotations for them. You use KMS. Of course, it costs a little bit extra. Of course, it's an extra pain to remember where your keys are, who has access to them, the policies for the key, the policies for the buckets, all of that. The Glue will need access to the key with which your business data is encrypted as well. But it's a more like you have control over what keys are used, and you can use different keys for different places as well. So that's quite nice. And continuing on the Athena and Glue subject, like data analytics in AWS, in Athena you have work groups. And that is a way for you to create those trusted research spaces without having to manage multiple AWS accounts and without bothering what data sits where. You can just have your AWS account with your data and create work groups for different purposes. On this example here, we have data science, sales, and corporate BI. And you have on the left different buckets, like clients, orders, and products. What you do then, you create IAM roles for the different work groups. Like each work group gets its own IAM role. To that IAM role, you allow access to only the bucket, only the data to which this group needs accessing. So we're looking at the example of sales. You have a work group for sales. You have configured different, that's also something quite nifty about work groups. You can configure different purposes of these work groups, and you can limit the bytes that they can query so that your budget doesn't get blown up. You can configure default encryption for them. You can configure like logs and metrics automatically for them. Quite nice. And your analysts come in and they don't have to worry about all of that because that's already done for them. And then your sales group, they get a work group, cool. They get a resulting S3 bucket, the space into which the results of their work will go, like the transformed data, for example. Their own log space, and also sales. They need access to the orders data, so you give them access to the orders data. They log in using this IAM role, and they have no idea what else exists. They don't care. They have their own space for doing their work. Happy days, everyone is happy. Now, we've touched a little bit on encryption. Let's talk about it a little bit more, specifically in the focus of de-identification of data. Because let's be honest, you can build an amazing data platform, amazing infrastructure. Your IAM roles are spotless. Your service accounts are all managed. You have workload identity federation everywhere. Lovely. But I guarantee you that your data engineers and analysts will spend a whole load of time battling with compliance, trying to convince them that accessing PII is okay and accessing data in general is okay. They will spend hours and hours and hours. And we have techniques to make that task easier. Techniques around anonymization, techniques around de-identification, masking the data that is maybe a little bit more sensitive. Because analysts don't always need access to your full set of sensitive data. They don't really care what the name of the patient is or the name of the person and the credit card number of the person that made an order. They don't really care about that. The different techniques that we have kind of can be grouped into 3 different areas. Reduction, which is where you replace the sensitive data with some string. Masking, meaning you mask the data somehow. And encryption. Encryption can be reversible and non-reversible. And we'll look at like very simple examples, names, ages, postcodes. The way your sample inputs and outputs would look like with these different techniques. With reduction, like I said, it's just replacing the sensitive value with a string, in this case, the word redacted, cool. Bucketing is another one, very commonly used in social research and population research and healthcare research. You replace a specific value with a bucket into which that value falls. For example, age 34. The bucket is 25 to 35. Postcode, this is a British postcode, and in the UK, very often a full postcode points to a specific house. So this postcode points to a house where this person, 34 years old, lives. Instead of putting the entire postcode, you just say SE10. This is a London postcode, Southeast 10. That will point to an entire neighborhood. So you have widened the choice where the data is. It might be like an area code, or like you replace the city with a state. Things like that. Make it more general, and you have different levels of granularity on bucketing, and that's up to you how you decide the level of granularity. Is a neighborhood too specific, too precise? Are you researching on a very rare disease, and knowing the neighborhood and the ethnicity, for example, will give you the exact identity of the person? Those considerations. Cryptographic hashing. Guess what it is? Replaces the data with a hash. And format preserving encryption is a cool one because it preserves the format of the data but replaces it with an encrypted string. This is really important for building those large language models, for training models, for building data pipelines, because then you can work with the exact format of the data without knowing the data. And this specific method can be reversible, meaning that if someone does have access, if you have a subset of people who can have access to PII, you can give them access to the keys, they can decrypt the data and have access to that. And that's also something, like I often get questions of like, well, how do you convince compliance? And that's how you do it. You start small. You start by removing all of your PII from the data sets and only giving analysts access to anonymized data. And then you show the value of giving analysts access to any data. They start doing their work, they start bringing value, they start influencing the business decisions with real data. And you see those results, you see the business impact, and then you can start a new conversation being like, oh, hey, maybe we can have a subset of people with higher level clearance, and they can access some more data because that is going to be valuable for this product. And we can serve our customers better and our revenues will go up. It's a step-by-step process, very long, very grueling, but you can start very small and then build up from that. BigQuery, for example, in GCP has integration with Cloud DLP, Data Loss Prevention service. This service gives you all of those data masking techniques. And one warning, it's expensive. but it plugs in, and you can forget to worry about have you copied the data, what's the view that people get, where is my PII, where is my non-PII. You just store your raw data in a data set, and you give people access with Cloud DLP masking the data that you want to mask, or like redacting or encrypting it, and so on. Things like column level access also helps, field level access also helps. And speaking of field level access, if you do use Kafka, you now start having techniques around field level encryption, and that's really cool. For Kafka Connect, it exists, like client-side field level encryption. Kafka Connect is like an intermediary between Kafka and your clients. With Kafka specifically, your brokers will see everything. So if someone compromises a broker, well, they will see the raw data. But you can now client-side encrypt, and while before you had to encrypt the entire data frame and you lost the structure of the data frame, the schema is lost, everything is lost, you don't know what it is. Now you can do field level encryption, and there are projects like Kryptonite that allow you to do that, and that's really cool because, again, schemas are really important for building up those data pipelines. For building up those models and training them, you need to know at least what the format of the data is and what the schema is. You don't need to see the data, so preserving the schema is really, really, really important for it. And I will finish this on my favorite thing to finish security talks on. Please disable public access to your buckets. In the previous talk, we saw a case study about publicly accessible buckets, and you would be surprised. This is a screenshot from a service that I Googled. It's available online. You can Google it. And it gives you access to all of the publicly accessible buckets. 375,000 AWS buckets. I really doubt that everyone who created those buckets meant them to be public. Sometimes you mean the bucket to be public, but 375,000 and 160 GCP buckets, so 160,000 GCP buckets, 100,000 Azure Blob Storage buckets, I doubt it. And this very service that, again, you can Google and find, allows you to look up files in those publicly accessible buckets. I was curious to see if there's any credential files in them. And of course there are. I was also curious about IDRSA. That's a very common name for encryption keys, and there are. Some of them granted, .pub, fine, public keys, not extremely mad about that. But some of them are not .pub. Some of them are private keys, and people put their private keys into publicly accessible buckets. SSH keys as well, along with some SSH configuration. And you can, this is a screenshot of like a video of just looking them up, but you can actually access those buckets and download those keys and configurations, and off you go. So please remove public access to your buckets. You can do it on the organization level, both AWS and GCP. You can have an organization policy that prevents people from creating buckets. In GCP, in order to make the bucket publicly accessible, you need to give access to all users. AWS, it's just public, just like that. So you can prevent people from creating publicly accessible buckets on the org level. And with that, I thank you very much for your attention. And if you have any questions, I'm glad to answer them. Thank you. Silence. Everyone is thinking about their buckets.
Hey, good presentation. One question though, with the AI models coming up and training models coming up, there is a constant ask of using the real-life data in training models, right?
Yeah.
So what is your response to it? And we kind of tried to do by case basis, but is there a general guidance or awareness or anything that Mandiant and other tool is working on to address that situation?
Right. Real-time data, yes, that is difficult to do, and it is a big question in itself. Do you need access to the entirety of your real-time data? maybe not. Well, once you're working on creating the model, right? You maybe can give, like the general guidance is to give access to a subset of data, or maybe a anonymized, like de-identified data might be okay as well. Not in all cases, of course, sometimes you need more, but like you generally don't really need access to the entirety of the data set. Real time, yes, but maybe like give access to a subset. Maybe give access to some columns. Really thinking, and of course your data scientists are gonna say, no, we need access to everything, all of it now. And try to work with them to understand what exactly they need and giving them access to a subset of it. And then once your model is trained and it's ready for production, then of course you can run it on like a larger data sets, but it's not, humans are not looking at it. It's just the process that is running and it's been vetted and all of that. Any more questions? All right, let's go for a break then.